All right, welcome back. You know those incredible AI models like ChatGPT? Well, today we're popping the hood. We're going to get our hands dirty and really deconstruct the engine that makes them tick. We're talking about the transformer, and specifically the part that does all the heavy lifting, the encoder block.
You ever stop and wonder, how do these things really get what we're saying? Like, how do they actually understand language? It feels like magic, right? But it's not. It's actually a seriously clever piece of engineering.
And here it is. This is the blueprint. I know. It looks like a total mess, kind of like a crazy circuit diagram. But seriously, don't sweat it. We're not going to try to figure this all out at once. Instead, we're going to build this thing together, step by step, from the very beginning.
Okay, so first things first. We've got a pretty big problem to solve right off the bat. Computers, they don't do words. They do numbers. So the first challenge is, how in the world do we get our language, our words, into a format a machine can even begin to understand?
It's actually a three-step dance. Let's take a simple sentence, like, how are you? First up is tokenization. We just chop that sentence up into individual pieces. How are you? Simple enough. Then comes embedding, where each of those little word tokens gets turned into a big list of 512 numbers. That's its vector. But wait, that loses the order. So the final step is adding something called positional encoding. This is what tells the model which word came first, second, and third.
So this whole embedding thing is super important. The best way to think about it is like this. Imagine a giant invisible space where words live. Embeddings are like the GPS coordinates for each word in that meaning space. So words with similar meanings like, say, king and queen, they're going to be neighbors. But king and cabbage, they're going to be miles apart. It's how the machine gets a vibe for what a word means numerically.
But there's a pretty huge flaw in this plan. With these basic static embeddings, a word like bank has the exact same set of coordinates whether you're talking about a riverbank or money bank. The model has no idea. It's completely blind to context, and, well, that's a massive problem.
So that leaves us with two giant questions we've got to answer. First, how does the model figure out the difference between the two banks? That's the context problem. And second, how does it know that the cat chased the mouse is totally different from the mouse chased the cat? That's the word order problem.
Okay, so I gotta come clean about something. A minute ago, when I said the input was just the word embedding, yeah, I was kinda lying. There's a little secret ingredient we add right at the beginning that helps us solve that whole word order issue.
And the solution is actually pretty clever. We literally just add another vector, this positional encoding vector, right on top of each word's embedding. This new vector is totally unique for each spot in a sentence. It's like stamping each word with its position number, first, second, third, and so on. And just like that, word order problem solved.
All right, one problem down, one to go. Now for the big one, context. And to solve this, we need to talk about the absolute game-changing idea that gave the original paper its legendary title, Attention is all you need. Seriously, this right here, this is the beating heart of the transformer.
So what is this self-attention thing? Well, it basically lets every single word in a sentence look at every other word and ask, hey, how much do you matter to me? So if you have a sentence like, the fruits were on the furniture, they tasted amazing. Self-attention is what helps the model go, aha, they is definitely talking about the fruits, not the furniture. It builds this web of connections, creating a truly context-aware understanding. But think about it. Language is just so complex, right? There are so many layers. Is looking at a sentence from just one angle, with one single attention mechanism, really going to be enough to catch everything? Probably not. And there's this great analogy for what comes next. It's like building a computer. You know, having one stick of RAM is fine. But if you want to multitask and run a bunch of complex programs all at once, what do? You pop in more RAM modules. And that's exactly what we're about to do with attention. This upgrade is called multi-head attention. And it's exactly what it sounds like. Instead of having just one attention mechanism, we run a whole bunch of them at the same time, in parallel. Each head can learn to focus on different kinds of relationships. Maybe one head gets really good at spotting who did what to whom. Another might focus on how things relate in time. It's like having a whole team of specialists analyzing the sentence all at once. So, how many of these parallel heads did the original paper use? They used 8. That's right, 8 separate attention mechanisms all running at the same time, each contributing its own unique perspective to build a super rich understanding of the sentence.
Okay,
So, we've got our input sorted, we've tackled word order and context, we're feeling pretty good. But now we've hit a new challenge. We're building a really deep network, stacking layers on top of layers. And deep networks, well, they can be a real pain to train. We need to add a couple more components to give it some stability and, well, power.
And this is where the add-in norm layer comes in to save the day. This little guy is a lifesaver. The add part is what's called a residual connection. Think of it like a highway bypass that lets the original signal skip past all the heavy processing. This is super important for training because it stops the signal from getting weaker and weaker as it goes through layers. Then the norm part, that's layer normalization. It's like a bouncer that makes sure none of the numbers get too crazy, keeping the whole training process stable.
But hold on, we've got one last problem to fix. So far, everything we've done, all the math, has been what we call linear. It's basically a lot of fancy multiplication and addition. And that's okay for simple straight-line relationships. But language isn't simple. It's messy, it's complex, it's non-linear. Our model, as it is, just can't learn those really tricky patterns.
The solution? A surprisingly simple but really powerful little component called a feed-forward network. Here's what it does. It takes our vector, which has 512 dimensions, and bam! It blows it up into a much bigger space, 2048 dimensions. In that bigger space, it applies a simple nonlinear trick called ReLU, which just means if a number is negative, make it 0. And then, just as quickly, it squishes it right back down to 512 dimensions.
So you're probably thinking, wait, why on earth would you expand it just to shrink it again? And that's the key. It's during that brief moment of expansion, in that bigger space, where the model gets to use that nonlinear ReLU trick. That's the secret sauce. That's where it learns all the complex, messy relationships in language. It's a quick detour that adds a ton of brain power.
And that's it. We have all our parts. We've got our input embeddings, we've got positional encodings for order, we have multi-head attention for context, we have add and norm for stability, and we have the feed-forward network for nonlinearity. It is time for the final assembly. Let's put this whole thing together.
And there we have it. Let's trace the journey. Our input vector comes in. First, it goes through the multi-head attention layer. Then it hits an add and norm layer. The result of that flows into our feed-forward network. And what comes after that? You guessed it, another add and norm layer. And that right there is one complete, fully functional encoder block.
But of course, why stop at one? In the original Attention is All You Need paper, they didn't just build one of these. They stacked 6 of them, one right on top of the other. The output of the first block becomes the input for the second block, which feeds the third, and so on, all the way up. With each layer, the model's understanding gets deeper and more sophisticated. So there you have it, we've just built the encoder. This is the part of the transformer that's all about reading and understanding. It takes our sentence and turns it into a rich, context-aware set of numbers. But understanding is only half the battle, isn't it? How does the model take all that understanding and use it to actually write a reply? Well, my friends, that's where the decoder comes in.